Simple harmonic motion. Consider a mass on a spring, and the mass oscillates, it goes up and down. Now let y be the displacement of the mass relative to the equilibrium. So if the mass is above the equilibrium, then we assume that y is positive, and if it is below, then y is negative. And we assume that there is no friction, so the oscillation goes forever, and such motion is called simple harmonic motion, as opposed to, say, damped harmonic motion. Now it can be shown using laws of physics that the displacement y can be described as a function of time, either as a cosine or as a sine curve. So if the maximum displacement occurs at time equal to 0, so if this mass is pushed to the top and then released, then it is the cosine curve rather than the sine curve, and the equation of motion is y equals to a cosine of 2 pi ft, where a is the amplitude, f is the frequency, it is the number of cycles per unit time, usually per second, and p is the period, it is the reciprocal of the frequency, and p is equal to the time needed to complete full cycle of oscillation. Now it may happen that the motion starts at the low point, so if the mass is released from this position in the bottom. In this case, the equation of the displacement is negative a cosine of 2 pi ft. Now it also may happen that the mass is pushed from the equilibrium, so if it is pushed up at time equal to 0 and then it starts going up or down, then the motion is described by the sine curve, so it starts at displacement equal to 0. Or if it is pushed down at time equal to 0, then it is described by sine curve but with a negative sign. Now consider the following problem from the textbook. It's page 208, problem number 9. It's given that the frequency is 1.5 cycles per second, the amplitude is 4 inches, and that the maximum displacement occurs at time equal to 0. So in this case, so since the maximum displacement occurs at time equal to 0, we can say that it will be a cosine curve that describes the motion. So y equals to a times cosine of 2 pi ft. It's given that the frequency is 1.5, so we substitute 1.5 for t and 4 for a, and this gives us that y is equal to 4 cosine of 3 pi t. This is the equation of the motion. What is really important about this equation is that we can tell from it where the mass is going to be at any time. So if you want to know when it will be, say, in 10 seconds, you just plug in t and evaluate the cosine. Another problem. It's page 208, problem number 13. It's given in the problem that the amplitude is 2 centimeters, the period is pi seconds, and that there is zero displacement at time equal to 0. So at the time equal to 0, the mass was in the equilibrium. So from this condition we can tell that it will be the sine curve that describes the motion. So the equation is y equals to a sine of 2 pi t over p. So I'm writing here p rather than f because it is the period rather than frequency that is given. And by substituting the values, a equal to 2 and p equal to pi, we get y equal to 2 sine of 2t.